Hi everyone, today we're going to talk about designing safe elevator systems amidst a pandemic. The elevator capacities has been drastically reduced due to the requirement of social distancing during the COVID-19 pandemic, and this reduction is a very serious concern as there could be large queues to be built up in the lobbies. So in this work, we use simulation models and to evaluate and propose some very simple interventions to improve the performance of the elevator systems that can reduce the waiting time and the queue length in the lobby. So we mainly propose two interventions. The first one is cohorting. So in the first graph, there is a queue manager that try to find other passengers who are going to the same floor as the first person. And if there's still some capacity in the elevator, then the queue manager will move to the second person in the line and try to find a cohort of passengers who are going to the same floor. The other intervention is called queue splitting. That is, the queue manager will set up separate queues which serves different floor ranges, and the queue manager will try to load the elevator from those queues in a round-robin fashion. Our simulation model is based on a very large government building in New York City that has a quite heavy traffic every day. So we simulate the passenger arrivals randomly and compare the performance such as waiting time and queue length to the benchmark, which is the first come first served, where the passengers who arrive at lobby first will enter the elevator first. And this is the default policy with no intervention.
Okay, hi, I'm Mali. I'm going to explain the results. So we simulated 100 independent random scenarios, and we're reporting the average performance on a Monday morning. In the first graph, I would like to call your attention to the figure on the third column, so which talks about queue length versus time. The x-axis is time, 8 a.m. to 10 a.m. If you see the default first come first serve, which is no intervention, will lead to a huge buildup of queues, especially at the end of rush hour. There might be 160 people in the queue. And if you do queue splitting into two queues, then there likely only to be around between 15 to 20 people in the queue, irrespective of when you arrive. And if you do the cohorting intervention, then it's likely to be only between 10 to 15 people in the queue. So this has the best performance in terms of what is the queue length. And the second graph is about queue length for different policies. So we see that we are going to try and split it into 2, 3, 4 queues, and we see that more queue splitting is better. And of course, if you look at cohorting, it really, really performs well. And we move on to practical issues where we see that even though more queue splitting is better, you need horizontal separation between all these different queues, 6 feet separation as well. So that is going to be a challenge. So in practice, we may not be able to do as many as we want. And there's another practical issue when we do cohorting is that the queue manager cannot really talk to the more than 15, 20 people in the line. It might be a huge number. So for that, what we propose is instead of trying to find as many people as possible going to the same floor, we just try to pair people up. So when ask the first person, see if there is a second person, and then load the elevator, and then so on. So this is called cohorting with pairing. And in this graph, you see that x-axis is number of passengers within the reach of the queue manager, and y-axis is average queue length. We see that if the queue manager can just reach something between 10 to 15 people, then this cohorting with pairing intervention works really, really well as well. So these are our two major interventions we propose. One is cohorting and queue splitting, and they do not require any programming of the elevators, and they work for large, small, and medium-sized buildings as well. Thank you.